This is AP Calculus, section 3.2, page 1. Today we'll be starting to talk about differentiability. And differentiability asks, can the derivative of a function be found at a certain point? Can the derivative of a function be found at a specific point? Or does the limit as h approaches 0 of f of x plus h minus f of x all over h, does that limit exist at the point in question? And in order for this limit to exist, then we know that the limit as h approaches 0 from the left side has to equal the limit as h approaches 0 from the right side. And this notation right here is looking in the left side. So this is f prime from the left side of whatever value you're looking at. And this is f prime from the right side. So does the slope of the tangent from the left equal the slope of the tangent from the right? Visually, there are 4 ways in which a function can fail to have a derivative at a point, so not differentiable. And the first one is if we have something like that. This is a corner. And here we have f prime from the left side of A does not equal f prime from the right side of A. And these are specific numbers. So this one may be a -2 and this one a +3. So very definite, specific slopes but different numeric values. Another way a function can fail to have a derivative is something called a cusp. And in this case, f prime from the left side of A approaches +infinity. And if you look at this, slopes from the left side, it's a small positive slope. As we move closer to A, the slope of that tangent line gets more and more and more positive. So f prime from the left side heads toward +infinity. F prime from the right side of A heads toward -infinity. And look over here. The slope is a small negative number, and as we get closer to A from the right-hand side, those slopes get steeper and steeper and steeper, so more and more negative, approaching +infinity. Since these are going different directions, we know that f prime at A does not exist. Oops, I think I ran over. Let me move that paper over for you. There you go. It does not exist. All right. The next situation is something called a vertical tangent. And this one looks like that. And the point that we're looking at is right here. It's some A comma f of A. It's really hard to kind of line it down here because it runs on top of itself, or appears to run on top of itself. If we look here, f prime from the left side of A, slopes here, small positive, gets bigger and bigger and bigger and bigger and bigger, very steep, These are heading toward positive infinity. F prime from the right side of A, small positive slope, but moving this way, moving from the right toward A. Those slopes are also getting bigger and bigger and bigger, more steep. So heading toward positive infinity. This tells us that F prime at A is positive infinity. Really, that means that this limit does not exist. And that goes back to when we were doing limits, that limit does not exist. We gave more information about it by saying that those values head toward positive infinity. So they increase without bound. There is no limit there. Now I do want to caution you about this point, a comma f of a, is that this function is not differentiable at x equals a. It's not differentiable there. The derivative does not exist. But there is a tangent line at x equals a. It's a vertical tangent. Hence the name vertical tangent. In the last situation where a function can fail to have a derivative at a point is if we have some kind of discontinuity. So we have a discontinuity there. Now that means that the limit as x approaches a from the left does not equal the limit as x approaches a from the right. I'm not talking about slopes of tangent lines here. I'm talking about the y values on the function. The y value from the left side does not equal the y value from the right side. Nothing to do with slopes. Thank you very much. Please join me on page 2.